Hey everyone. First of all, my apologies. I've been losing my voice a little bit, so I'll be taking frequent breaks to take a sip of water, and if my voice cracks, I'm very sorry. Oh, that's perfect. Thank you. So I'm going to talk a little bit today about Godot's renderer. First of all, a little bit about me, like why is this guy up here talking about Godot's renderer? I'm the lead rendering maintainer of Godot. So basically what that means is I organize weekly meetings for the rendering contributors to talk about what they're working on, give feedback on what they're working on, and plan out on what they'll work on next. I also pretty much review every single pull request that touches the renderer. So I've got a good familiarity with what's happened and what's being worked on right now. I'm also a board member of the Godot Foundation, so I've got a pretty good love for the project. During the day, I work for W4 Games on their console ports, and I'm pretty much living the dream of every open source developer, where I work for a company that lets me work on the project that I love with a lot of my working hours. So thanks to them, I get to spend a lot of time working on the renderer, even though W4 Games doesn't sell the Godot renderer. We sell console ports, but they let me do a lot of that work. Now, generally, these are the topics I'll be covering. So I want to give an update on the last year. If you were at my talk last year, I talked about all the things that the rendering team is excited about and the things that we want to be working on over the last couple years, over the next couple years. And now what I'm going to talk about is what we actually did over the last year. So which of those things we actually covered. I want to talk a little bit generally about the state of the renderer, where I think things are right now, what I think Godot is a good fit for right now in terms of rendering capabilities. And then I also want to talk a little bit about what we're working on right now and what we're going to be working on in the shorter term. And I don't mean short term, I mean, once we've finished with what we're working on now. So kind of the medium term things. And also, I'm going to have a long Q&A session at the end, so I hope that's good news for a lot of you. If you have questions, there should be time to ask them, so I hope that goes well. And finally, what you're going to see in this talk, especially as I talk about what we did last year, the theme of the talk is really not big, exciting features today. The theme of the talk is very important bug fixing, polish, and foundational improvements, because that's what the last year has looked like for the rendering team. We've done a lot of things that aren't really that sexy unless you're a graphics engineer, and it's mostly just stuff that really makes sure that we can ship a solid experience, and we have a really nice foundation to build on. Now, to that end, this is a bit of a tongue-in-cheek joke made by a rendering contributor recently, but I do think it exemplifies kind of the attitude of rendering contributors right now. We have, of course, every time Unreal announces a new feature, we have somebody coming on and asking us how many days until we have the same feature. And you don't see a lot of excitement from the team about that, but when you have somebody making a real game, trying to release their game and running into roadblocks, then you see the team really step into gear and get excited, like, okay, we've got to do something, and then people really start to put some momentum and some effort behind that. And for me, I find that extremely exciting, because we're in a state now where we have so many people coming to Godot, and we're seeing more and more games released each year, and so I want to make sure that all of those people are actually getting their games out the door, and they're not finding out towards the end of their game that all of a sudden they can't finish their project because there's some bug they can't work around. So here are the things that we did last year that we talked about last year. So first off, we finished, and I'm saying that in parentheses, the compatibility backend. So this is our low-end renderer aimed at older devices. It was missing a ton of features last year, and we've finally finished all those features that we have planned for it. We're calling it feature complete at this point, but feature complete doesn't mean that it has every single feature under the sun. Feature complete just means that it has all the features that we had planned for it when we were designing Godot 4. So it's a much more limited set of features compared to the Forward Plus renderer, but they're there now, and we'll work on more over time. Next was the acyclic graph. Now this is something I talked a little bit about last year. We have a great, very technical blog post on the website if you're interested in that sort of thing. I'm going to just hand wave and say it was a huge amount of work. It was really amazing. And for most people, the only thing you'll notice is about a 10% performance improvement. But it also solved tons of nearly impossible to track down bugs that were coming from our Vulkan backend. This was a huge piece of work, and it really, really is a big part of the reason why Godot 4.3 feels so much more stable than Godot 4.2. And then next, this is something that we've just merged for 4.4 is background pipeline compilation. And again, I talked about this quite a bit last year, so I don't want to provide too many details, but a lot of people, especially if you're working in 3D, are familiar with the shader stutter problem, which is you show something in the scene or you look at something for the first time in the scene and all of a sudden you get stuttering because the shaders are being compiled for the first time. Now in reality, it's not the shaders being compiled, it's something called the pipeline being compiled. Again, I'm not going to go into too much detail, but we have mostly resolved that problem now, and more importantly, we've crafted a system that allows you to address the problem without doing the typical workaround, which was behind a loading scene, show every single object in your scene for one frame with every single combination of lighting or VFX or whatever you have with it. You don't have to do that anymore. But there is a catch. No, it's not much of a catch. The catch is everything that you want to have pre-compiled has to be in the scene tree. So if you want to show a mesh at some point during the frame, make sure that you have it in the scene tree and visible, and then we'll be able to pre-compile the shaders and there won't be any stutter, and then just set it to visible. So instead of loading things dynamically, you just have them in your scene already, and that's it. Okay, a couple exciting things. We have a Metal and a D3D rendering backend now. This is great. Metal in particular makes Godot run way faster on Apple devices. The D3D backend also helps Godot on Windows devices, but more importantly, it's necessary in order to run Windows on run Godot on Windows ARM devices. They don't support Vulkan, they only support D3D12, so it unblocked that. Both of these are things that we've wanted for a long time and finally got finished, and they're huge amounts of work. We finally added render hooks, which is something I talked about in detail last year and won't go into now. And we're almost finished with shader templates, and this is, again, something I talked about last year. And finally, temporal optimizations to shadows. So what you can see on the left is what shadows look like now in 4.3 or 4.2. If you are using them and zooming in as far as you can possibly zoom, you'll see how they look. And now with TAA or FSR 2.2 enabled, they look like how they look on the right. So very, very smooth. And this is, let's see, probably about a centimeter. The zoom level is about a centimeter, so they look quite good when you're looking from a reasonable distance. Okay, so these are the things we did last year that we didn't talk about last year. So we overhauled the rendering device. This was something we found was very important while working on the D3, D12 and Metal backends. We realized that we were duplicating a lot of code that was in our Vulkan backend, so we abstracted everything out to what we call a rendering device driver, and this made the work necessary to implement D3, D12 and Metal way, way smaller, but it also just meant that everything is easier to maintain for us in the long term. So this took many months to get right, and it was a ton of work for contributors, but in the end, it's going to save us a lot of headache in the future. We added batching to the RD backend. This is 2D batching, and that makes the RD backends, are the forward plus and mobile backends. It makes them about as fast as the compatibility backend in 2D now, which is really good for devices that don't support OpenGL. We also finally re-added vertex shading. Now, if you're not familiar, vertex shading is what you see on the right. It's something that you're very familiar with if you were doing graphics on the PlayStation 1, and a lot of people want to have that kind of style in their games, and there's no substitute for it. You can't fake it, you just have to have the feature. It's something we supported in Godot 3, and then we kind of lost it in the rewrite to Godot 4, and it's finally back. The other thing is, for certain situations, it can also be quite a bit faster than normal lighting. So it's there, it's finally back, and it's been long awaited, so we're happy to have it back. And then we did a lot of optimizations. I'll show a few of them here. First off, you probably can't read that, but that's intentional. We added shadow volume culling. So what this does is it detects if the shadow is going to be visible by the main camera, and if it's not, we just don't render that shadow at all. Then we also added a tighter back buffer recs. We merged passes in the Vulkan mobile renderer. We improved our MSAA usage bits, and on 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 and on. And these are just my favorites, by the way. This isn't even a fraction of the different things we did. Importantly, though, and the point I'm trying to make is a lot of work has gone into little things that just improve the renderer rather than big and exciting features. All right, now here are the things we didn't do that we talked about last year. We didn't finish making all the temporal improvements that we wanted to now that we have good temporal reprojection. This is things like SSAO, SSR, and SSIL. This is really important to us, and it's something I talked about last year that we didn't do. Really what we want is to go from the left to the right. This is an example from Intel. On the left is the SSAO technique that we use, and on the right is the one that we want to use. The one on the right takes about half as much time to calculate, and it looks much, much better, but it relies on temporal reprojection, and we just don't do that at all. So this is something we'd like to do, but haven't done yet. We didn't implement a deferred renderer. We didn't finish overhauling SDFGI. A lot of progress has been made, but it's not finished. At this point, we're going to start calling it HDDA GI, but in the editor, it's just going to be called dynamic GI, so if we change the underlying algorithm again, we don't need to rename the technique. So start to get that into your head. Eventually, we're going to have a feature called dynamic GI, and it's just the feature that we used to call SDFGI. We also didn't implement resource streaming. We have a lot of VFX improvements that we want to make. We're still figuring out the details of what we want to change. Unfortunately, this year we didn't do a whole lot in that area, even though it's something that's really important to us and we'd really like to improve. And most of the compositor features that we talked about last year we haven't done. That includes multipass rendering, custom buffers, and things like that. All right, and now here are the things that we didn't do that we also didn't talk about last year. No, I'm just kidding. I'd like to talk a little bit about the current state of the renderers now. So for 2D, I mean, I hope lots of you have tried the 2D renderer. It's great. I think it's quite easy to use. It's fast, it's flexible, especially now that we have 2D batching in the RD backends. It's very efficient. It's suitable for most 2D projects unless you're doing something very, very highly specialized. It's going to be fast and just handle whatever you throw at it. So for us, it's time to start to work on more advanced things. And I don't know what that is. Maybe it's enhanced lighting. You know, our lighting system is pretty simple, and it hasn't really changed all that much in many, many years. Maybe it's something better animations, or maybe adding some way to integrate third-party solutions like Rive or something like that, so that we can get some other workflows there. I don't know what that is. That's something that I'd love to chat about, and if you're interested in 2D rendering and want to propose things and talk about it, then join our rendering meetings and get involved. And then this is a picture of the sort of thing that you can do with our 2D renderer. This is Halls of Torment. Fantastic game. It's released already, so you can go and buy it. But you can see there's tons of stuff there. There's particles, there's tons of animated enemies, there's a UI, everything looks great, runs great. You know, it's doing really, really well. Now, 3D is not quite the same. The 3D renderer is good, but really only for small or medium-sized projects. And by that I mean projects where the entire level fits in VRAM. So if you can load your whole project and it only takes 2 or 4 gigabytes or something like that, then it's great. It's going to run well, it's going to perform well, it's going to look good. Hopefully, if you have good assets, it'll look good. But if you want to go bigger than that, if you want to have something that is really big or really dynamic, then Godot's going to start to struggle. And by that I mean the renderer is going to start to struggle, because it works under the assumption that everything is fitting in VRAM comfortably. And that's a huge limitation that we need to unblock. And the core workflow for working with 3D still needs polish. A lot of things from effects to shaders are a bit cumbersome, and we need to make those things better as we have more and more 3D games made with Godot, and as people are making bigger and higher quality things. And you know, this is restating the same thing. It's just not good for open worlds or massive levels right now. When you go online, there are a lot of people saying, oh, of course, you can do anything in Godot, just code it yourself. Well, I don't think that's true when it comes to the renderer. You will hit fundamental limitations with the renderer that will block you from making the next Fortnite in Godot. And that's just the truth, and it's something that will be unblocked over time. Now, luckily, there's a lot of low-hanging fruit for performance, and I'm going to talk about that a bit later. Now, I've been a bit humble because the truth is you can make something really nice in Godot. If you were around yesterday, you might have seen PVKK or seen it up there, and you can make truly nice-looking games in Godot. But there are limitations that we want to unblock. Okay, so what are we working on now? A lot of performance enhancements are coming down the pipe for 4.4. I talked about some earlier, especially for mobile devices. Also, we're going to be doing a lot of things to take advantage of the Uber shader, which is that part of the background pipeline compilation that I talked about before. Also, expect to see a lot of bug fixes. There's a lot of things in the pipeline now, a lot of people working on different things. And finally, just one fun feature that you should expect to see fairly soon is 2D shader instance uniforms. So if you're this has been a very highly requested feature from people working in 2D. If you only ever touch 2D and you never touch 3D, you might not even know what this is. But this is a way to get data into your shader that changes per node without having to create a whole new material. You know, if you want to change a color or change some parameter in the shader, and it can make the workflow much, much, much nicer if you're doing shader effects. So that should be coming soon. So I want to talk a bit more detail about some of the performance enhancements we have planned. If you look at the most recent rendering priorities blog post, there's a link to our kind of rendering roadmap that has way more than this, but these are a few things that I'm really excited about that I'm certain we should be implementing soon. So the first is FP16. That's just a funny way of saying half precision floating point. I'm going to talk about this more on the next slide. Shader matrix optimizations. This is a funny optimization that allows us to do matrix multiplications a bit faster than we normally would. The next is batching together shadows and the depth prepass. This is a really interesting optimization that is a super low-hanging fruit just based on the way that Godot is designed. When we render shadows, we don't use the mesh that you've imported into the engine. We create a special version of the mesh with as little information as possible. So it's very lightweight. It just contains positions. And then when we render the shadows, we just use one special material because shadows don't need lighting. Shadows don't need any like UV effects or colors or anything. You just need to know the position of the object in order to calculate where the shadow is. So since we're using the same material and we're using a mesh with a shared format, a clever thing we can do is store all of these shadow meshes in one giant uber mesh and then render all of the shadows in one draw call. And we don't do that now. So if you've got an outdoor scene with a directional light, you could be rendering to the shadow map every single object in your scene. With this, you could be rendering everything in just a couple draw calls. And I say a couple because animated meshes and things like that still need to be rendered separately. But it should make rendering shadows way faster. And it's something we'd like to do soon. And then finally, the specialization constants. This comes from the Uber shader optimization I mentioned before. Specialization constants allow us to create specialized versions of shaders that cut out unneeded features. We've been avoiding this optimization until we finish the Uber shader stuff, and so now it's time for us just to hyper-specialize our shaders and cut out unnecessary components. Okay, so I want to talk a little bit about specifically the FP16 optimization. This is a really cool thing. So normally a floating point number looks like this. By default on most GPUs, a floating point number is going to have 32 bits and it's going to be laid out like this. But most GPUs support also using half floats or FP16 values. And so they do the same thing, but you can see they're an approximation. I mean, a floating point number is already an approximation, but these are an approximation of an approximation. These are kind of nice. On mobile GPUs and on modern desktop GPUs, you can process 2 FP16 floats in the same time that you can process a full float, which quite literally means that you can do your calculations twice as fast as long as you're consistently using half floats. And that's great. But there is a downside. If you look here, these are the maximum values you can store in a floating point number. When you have less bits, you just can't store the same range. So a half float can only go up to 65,504. What happens when what happens when your shader calculates a number that's greater than 65,504? Well, you get NANs. And for shader programmers, NANs look like black dots that spread all over your frame. And it's pretty bad. And you can't really recover from it if you're doing anything with temporal reprojection. You just lose your whole frame and everything goes black. So you have to be very careful and you have to take precautions in your shaders to avoid that from happening. So what that ends up looking like is a kind of a two-pass thing. First, you convert everything to use FP16, and then you have to go and make sure that you restructure all your algorithms so that you're never using values that are greater than 65,000. And sometimes that means actually doing a few more calculations or doing simple calculations in a few more steps. But because you're doing everything at double the speed, the extra few calculations don't matter all that much. So you have to be very careful, but ultimately it's a pretty nice performance benefit. On mobile, it's an absolute must. On desktop GPUs now, though, it's getting to be a pretty significant benefit as well. So it's going to benefit people quite widely. Now, I also want to talk about the shader matrix optimization. This is a very funny optimization. So if you take a very simple shader like this, this is a shader that does one thing. It multiplies a vertex position by some transform. And if you're familiar with writing vertex shaders, this is your bread and butter. This is, this could be rotating, translating, whatever. It's just a very simple operation. Now, this is another way of writing the same thing. And it means the exact same thing because in a transform like this, your final row is always going to be 0, 0, 0, 1. So these do the exact same thing. When I look at this code naively, without diving into the performance characteristics of either, I would think that this second version would just be a tiny bit slower. You've got an extra local variable, so maybe you might lose some performance because you're initializing a variable. Maybe you're going to lose a little bit of a performance because you're constructing some data type. But if you dive in and you look at what the compiler generates, and be warned, I'm about to show you what the compiler generates, you see this. So this is the first one. This is just a single matrix multiplication. This is what the compiler actually deals with. It's not one line of code anymore. It's a whole bunch of lines of code. But here is what the second version looks like. So I don't expect you to read all that, but I think it's pretty clear that the second version with the extra line of code is a lot less. And particularly what you're losing is this. That's a buffer load and 4 fused multiply adds, and you're trading that for 1 add operator. I'll just go through that again. So importantly, what's going on there is by specifying this manually in the shader, the compiler is able to see we've got those zeros, and anything multiplied by 0 is 0, so we'll just throw out those instructions altogether. And there's 1 at the end. Anything multiplied by 1 is just itself, so we'll just add that value on the end. We don't need to multiply it by anything. So just by making this one tiny change, we're actually able to significantly enhance the speed at which we do matrix multiplications. And we don't do this anywhere in the engine right now. We just do the full matrix 4 multiplication. And what this results in is about a 3% frame time improvement. And that's not a 3% faster matrix multiplication. That is, your entire game is running 3%, well, maybe not your entire game. The entire rendering frame is running 3% faster just because we're able to skip that much work. Now, this is only for bandwidth-bound scenes and on integrated GPUs, mobile GPUs. If you're running with an NVIDIA 4090, this probably won't make much of a difference because the bottlenecks are going to be elsewhere in your game. But it's an optimization that's well worth making. And for devices running on batteries, it also means you're saving a lot of battery life because you're avoiding doing operations that don't need to be done. So the real gains are going to be a bit smaller, but they're not negligible. Okay, so these are some of the things that we'll be working on soon. They haven't been started on, but they're quite exciting. We want to make a lot of changes that allow you to customize rendering more. These are those compositor tools that I talked about earlier, and I talked about in great detail last year, so if you have any questions about how we're going to make rendering more customized, check out my talk from last year. We're going to add streaming. As soon as we get somebody willing to take the time and implement it, this is a huge priority for us. And this is the first step in unblocking bigger scenes and more dynamic scenes where things are streamed in and out. I talked earlier about temporal improvements to screen space effects. This one needs to happen soon because especially for SSR, the quality is just not where we want it to be, and it's something that we want to have as soon as possible. We also want to make a lot of improvements to our light mapper. Right now, it's too cumbersome and doesn't look good enough. We know we can get it looking better, baking faster, and make it easier to use. And we've been working on it, but we have a lot more work that we want to do. Ideally, it should just be totally seamless. You should be able to map out your scene using dynamic lights and then bake it and have it just look better and run faster. And that's not the case right now. Right now, you still need to tweak things. You still need to, it's a bit finicky, and we don't want that to be the case. Now, one of the things we've added coming in 4.4 for the light mapper is a GPU texture compressor. So this is really important because right now we're not compressing the light maps, which means that they're huge. They take a lot of space, which slows down load times for games with light maps, and it actually makes the light maps slower to render. With texture compression, you can reduce the size of the light maps by 8 times, which ends up being really significant. But the problem is our current CPU-based texture compressor can take several minutes just to compress the texture. So if your bake time is a couple minutes and then the compression time is a couple minutes, your turnaround ends up being a lot. If you've got a really, really good GPU, your bake time might only be a few seconds, and then you've got to wait a few minutes for the texture to compress, and that's just not workable. Now that we have a GPU-based texture compressor, it's much faster. Here's a comparison from the pull request that added it. So these are just a few different 8K textures, but even here you're seeing going from a minute and a half down to a half a second. And it's about the same with light map textures. You go from several minutes down to, at most, a couple seconds. Next, we've recently implemented bicubic sampling of light maps. This is something we already had in Godot 3 and we've brought back to Godot 4. What this does is it just smooths out the underlying light map data to make things just look smoother and nicer. So on the left, you can see with bicubic sampling turned off, and on the right, it's turned on. I really like this image because you can see the reflections on the floor and stuff. That's not from light maps, that's from other systems. The light map part is the blocky direct lighting that you see there, and with bicubic sampling, it's much, much nicer. We also added anti-aliased shadows for the light mapper. And this is relevant mostly when you're doing a low-resolution light map and you're baking lights directly. Baking the direct light from them. So you can see on the left is before, then before plus bicubic. It's a lot smoother, but you still have bumps because the resolution is so low. And then in the after image, it doesn't show up all that well on the projector. In the after image, you can see it's kind of smoothed out a bit more, but you still have some evidence of the underlying pixels. And then once you apply bicubic to the after image, it looks really, really good. Okay, any questions?
Great talk, thank you. I sadly have 2 questions. First of all, the FP16, will it be in the background or something you have to do yourself? And the second one would be web GPU integration, if that's planned or not.
So it's something that'll be totally in the back end. This is an optimization we want to make in our internal shaders. You can actually get the benefits of FP16 in your own shaders by using medium P. It's a variable qualifier that you can use in GLSL, which we support in GD shaders. It's just a total pain pain to use, and since we're not using it on our end, it's not a huge benefit, because most of the work that's done in the shaders is done in our internal shaders. I don't know exactly what architecture on the desktop. I think for AMD it was RDNA 3 that really started to use or benefit from FP16. For NVIDIA, I'm certain the 4000 series benefits, but I'm not sure exactly where the line is there. So sorry about that. Mobile GPUs, everything benefits for, any mobile device you can get your hands on will benefit from FP16. Yeah.
Hi. Are there any plans to make reflection for compiled shaders available to the programmers? So seeing what the inputs, uniforms, and outputs, and so on for the shaders are, like from the compiled shader format from SPERF, when you load something from it.
I'm not sure if I fully understand the question. Is the question more about seeing what the shader looks like once it's been compiled, or just seeing...
No, when you load a compiled shader, I would like to see what it expects in which slot and what data types.
Right, and that's not for... You're talking about GLSL shaders or GD shaders?
Like the Vulkan intermediate format, like SPIRV or whatever, SPERF.
Well, I guess I can say we don't have any immediate plans. This is the first I've heard somebody asking for that, but if that's something you'd find useful, feel free to make a proposal with details about exactly what you're looking for, and then it's something certainly worth discussing.
Was just the WGPU thing that you missed? If that's a planned thing you want to do or not?
Sorry, is the question, do we plan to support WGPU?
Yes.
No, WGPU is a desktop implementation of the web GPU standard. It kind of does the same thing that our rendering device does, which is abstracting over Vulkan, D3D12, and Metal. So we don't have any plans to add support for that. We will add support in Godot for web GPU in the future, but we're waiting for the spec to be finalized and for support to be widespread across devices.
Hi, thanks for the talk. I wanted to ask about the GPU profiler and if there are any plans to get it working in Godot 4 again. Also, maybe I'd like to help out if I can get some pointers on that.
Yeah, the GPU profiler is working in Godot 4. It's significantly better than the GPU profiler we had in Godot 3. We've got a lot of ideas for ways to improve it more, but nobody's working on that right now.
Do you want to put some color on what you said, that the size of the project that the renderer is currently suitable for? Because everyone always thinks their project is bigger than a medium-scale project, right? So.
Yeah, that's a good question. What I had said before is something that fits within VRAM. That doesn't mean that like every single asset in your entire game fits in VRAM, but what it means is that everything that is currently loaded should fit within, whatever you're planning on supporting. So if your minimum spec GPU has 4 gigabytes of VRAM, then every mesh that you have in your scene and loaded, and all your textures and everything should fit within that. So when you have a game like PVKK, for example, to me that's like a really nice, polished, big game. But from a GPU's perspective, it's medium-sized, right? It's not an open-world game. It's not, it's not rendering kilometers of detailed vegetation and things like that. So that's kind of the point I'm trying to make is don't expect to have a massive open-world game with very, very detailed worlds or, a detailed city like Cyberpunk or something like that. But you can make a large game, but you have to manage your resources and manage your levels a bit more.
Hello. Oh, sorry. I just wanted to ask about recently released the FSR 3, if there are any plans. And one other question, maybe a little bit too farther into the future. Like a year or two ago, there were also a little bit some talk about ray tracing in the Godot. So just, are there any plans or how do you see it? Thank you.
Yeah, I think we'll support FSR3 eventually. I'm not sure if it's fully open sourced yet. I know components of it have been open sourced, but as far as I'm aware, not everything has been open sourced yet, which means we can't even get started on an implementation. The other thing with FSR3 is it requires a lot of big changes within your renderer in order to support it, and you have to hand over a lot of control over the rendering process to FSR3, which is very different from FSR1 or FSR2, which you can just plug in to your engine. So once everything is open source and available, then we can evaluate whether those are changes we want to make. I can say that a lot of us are really excited about it, so hopefully we'll see it, but until we can properly evaluate what changes are necessary, I can't really commit to one way or the other. As far as ray tracing goes, we'd love to have ray tracing support in the engine. I mean, right now, we don't even expose ray tracing through our rendering device, which just goes to show that we haven't even taken the first steps to supporting it, but it's something we all want to see. Every year, more and more of our users have devices that support ray tracing. I believe, and I'm working off of some fuzzy memory here, but in our latest poll, I think we found that about 40% of our users have graphics cards that support ray tracing. So it's starting to reach that significant point where it justifies adding it, just because enough people will be able to take advantage of it. But again, we don't have anybody working on it right now, but it's something we'd love to see.
To give you some motivation, I have a game that quite heavily suffers from poor screen space reflections. And especially on rough surfaces, my lights look really rough. I can show you screenshots. Do you have any good recommendations to work around this?
For screen space reflections, no. This is why I say it's something that's a really high priority for us, because it's a very particular kind of technique, and it should just look good in all cases. And right now, it looks okay in some cases and looks really bad in other cases. I guess the best workaround is going to be manually dealing with reflection probes. Reflection probes look great, but they're a pain to use. You have to, place them in a particular way. If you're already using voxel GI or SDF GI, you can get decent reflections, especially very rough reflections. You can get, out of SDF GI, you can get really nice rough reflections, but the cost might not justify it if you're not already using SDF GI.
So, hello. I do have a question, Clay, for you. But first of all, I would like to give a great shout out to the rendering team. They're doing an amazing job. So I think we can thank them. But this is a personal question for me. So I'm currently working on a game that is on the compatibility renderer for the web. So I was wondering, I know that the compatibility renderer is feature complete, but would it be technically possible to have decals, but even in a limited capability? Because I know that OpenGL is not the most favorable platform to do so, but is there something that can be done?
Yes. This is something I actually thought about quite a bit as I was writing the compatibility renderer and when we were first designing it. There are a few things that I would like to see added to the compatibility renderer. Decals is one of them. And you're right to point out it'll be a more limited form. It's not going to be as performant as Decals and the other renderers, but I'm fairly certain I have an idea for a way that it could work well. I'd also like to see eventually volumetric fog and SSAO in the compatibility renderer. Again, it's not going to look as nice as the other ones. It's not necessarily going to perform as well, but I'd really like to see at least those features added eventually. Yeah.
I could probably ask you that later as well, but what's the current state about mesh decals?
There's a proposal for mesh decals. It's a technique that doesn't make a whole lot of sense in a pure forward renderer. So the discussion that we've had so far has kind of been like, well, let's evaluate it once we have a deferred renderer, and then maybe it's something that if people want to use, we tell them, well, you can use it, but it's going to perform really poorly if you have the forward renderer enabled, so turn on the deferred renderer if you want to use them. Until we have a deferred renderer, I'm not sure it makes sense for anyone to spend a lot of time investigating them yet.